Today, I'm going to answer the question, what should Christians make of AI? Welcome to Missing the Mark, where we look for meaning in strange places. I'm Christopher. So, full disclosure, I'm answering the question in this format because this is the format I was asked, but very, very little of what I'm going to say has anything particularly to do with Christianity or Christians. About the most I can think of, really, is that Christians acknowledge that as human beings they have a duty to the truth. Lots of other people do too, and, but that's kind of about it. So there are two things that are meant by AI or artificial intelligence. One of these things is something that's just like us, but we made it. And the other is essentially anything like a tool or machine or what have you that accomplishes something that we would use intelligence to accomplish. Now, the thing is, everything that exists is actually in sense number two, that second sense, that it's a thing that accomplishes something that we would use intelligence to accomplish. It is not an intelligence like us. Now, it's not that it would be a tremendous philosophical problem for Christians if number one in fact did exist, because we already make intelligences. It's called reproduction. God gives it to us to take part in the making of things that are like ourselves. So if somehow we actually had the technological ability to create something like this, it would be basically it had the same philosophical problems that reproduction does, and it would just use different particulars to get there. And that wouldn't really be much of a problem, because reproduction isn't a problem for Christians. So, we make the body and God makes the soul. And, by the way, that's not a ghost in the machine kind of thing. I don't have time to get into the full, Orthodox Christian conception of the soul, but it's not like a ghost in a machine, like the little locust pulling on the levers. That's not at all what I mean. So, bear in mind, when I say God makes the soul, I don't mean that like God produces a ghost that then gets united to some particular machine. It's more complicated, more subtle than that, and just different than that as well. But anyway, but speaking very, very loosely, God makes the soul and then unites it to the body that we take part in making in reproduction. And so if we took part of it through technology rather than reproduction, okay, like that's not a problem. It's not any kind of challenge or anything. So I'm not saying this to defend Christianity. I'm just saying, like, as it happens, the particular types of AI that we have are not at all sense number one. Nothing thinks in the way that we do. It's all sense number two, plus some propaganda, basically. So I want to go over what sense number two really means, because that's the only thing you will actually find. And I'm going to start with really, really simple versions, because AI is nothing new. Video games have had AI for a very long time, good old Pong, if you've seen, it's like a tennis imitation where you just have the two things that move up and down and the ball goes back and forth and you have to hit it, and if the ball goes past, you lose a point. It's like how old is that game now? I don't know, 60 years old or something. Anyway, if it's not a two-player game, it's a one-player game, something moves the paddle, and AI, the artificial intelligence, it is doing a thing that an intelligence would do, and just doing it differently, because you would just have, various types of code that you would write that would just use information and calculate what move to do, and there you go. And the thing is, to really understand that kind of thing, it really helps to be a programmer. I'm a professional programmer, by the way. But to make this more general, I want to use an example. It's a lot simpler, in fact. So back in the day when metal coin money was actually worth something, you might want to, in more than trivial amounts, you might want to sort the coins that you have for, various purposes, but just to know how much money you have in coins, because it's easy to lose track. And a human being would use intelligence to do this. We'd look at the coins and put them into the appropriate kinds of stacks and count them and so on. Okay, but you can build a machine that will do that same thing and does not use intelligence in any way whatsoever. Now, you can do this with springs and levers and all sorts of moving things, but you don't even need to do that much. So I just want to discuss the simple version. These things existed. They used to exist, and probably still do for all I know, but I haven't seen one since I was a kid. There used to be plastic, but let's say we made one of metal. So real simple. Let's say you have a funnel, and it comes down, and then it orients the coins such they're falling basically in a slot, right? And then they come down and they come along a track, and then in that track you have progressively larger holes. So you have a dime size, I'm using US currency obviously, this will work for US currency, it probably works for other countries' metal coins as well. If you have multiple coins that are the same size, it won't. Doesn't matter, US currency. So you have a dime size one, and then a penny size, and then a nickel size, and a quarter size hole, and then a $half size hole, and a silver dollar size hole. Why not? And so what happens is that as the thing runs along, as long as it's not going too fast, if it's a dime, it'll fall in, but if it's a penny, it'll keep on going and then fall in the penny one. If it's a nickel, it'll keep on going and fall in the nickel one, a quarter in the quarter one, and so on. And then in these slots, you can then, as they go down, you can swap them so that they are then in appropriate order, because, you know, the dime is worth more than the penny and the nickel. And so you just swap them so they come out, and then you can sort of reorient and get them to fall down flat into into nice coin stacks. And then, you know, you'd have a door on the front that makes it easy to get at these things. And then you can, in point of fact, have, you know, gradations going up the side to indicate, you know, if the coins are this high, it's this much money, and this high, it's that much money. And so you have it's not even a machine, it's got no moving parts, you just have a piece of metal that if you pour the coins in at the right thing and hold it at the correct orientation within the gravitational field, you know, hold it upside down, it won't work. Do this in space, it won't work. But, you know, given the prerequisites of this thing, it does what human intelligence would do. Hopefully you can visualize this. It'd be better, obviously, if this were a scripted video and I had the thing, you know, pictures of the thing to show. But anyway, point being, you can imagine this, you can look them up. And this is a thing, is artificial intelligence by, you know, sense number 2 of a thing that does something that human beings would use intelligence to do. It has sorted the coins by by their increasing value and counts, you know, how much they are worth. You look at wherever the top is and there you go, that's how much it says it's worth. So, like, is that anything like intelligence in sense number 1? No, obviously not. It has no moving parts. It's just a piece of steel. If you were to melt it down into a block of steel, it would have all of the same properties, except it, you know, wouldn't be any good at sorting coins. So this, I think, really draws the distinction very clearly between sense 1 and sense 2. Sense 2 being, you know, it does something that, you know, humans would use intelligence to do, but it doesn't do it in the way that we do it. It doesn't look at them and understand the concepts and relate the concepts to each other and then implement this in the physical world. It's a bunch of tubes and slots and whatnot. So in like manner, when you have the AI inside of a computer program, it just consists of a bunch of lines of code where, like, if this number is greater than this value, then you do this, otherwise you do that kind of thing. And it looks basically like that. And I'm not going to go into the real details because that kind of AI is not very interesting. Just the one thing, and I mentioned this in my video about, you know, do we live in a simulation? And something to bear in mind is the AIs that you see in computer games, you don't render pictures for the AI and that the AI then does image recognition and manipulate. They operate in a completely, utterly different way. You just give them all of the information about, like, the actual 3D coordinates of the various things and their bounding boxes and what have you. And then you implement logic as to whether or not they can see each other, as in, like, when you draw a line in 3 space, do any of your objects intersect this line kind of thing. And there are lots and lots of techniques, but, like, it's absolutely nothing like what we do, not even slightly like what we do. It just gets rendered out in pictures. You know, so this is used to manipulate 3D models that get rendered into pictures, and so it looks surprisingly like, you know, like this guy knew that I, you know, saw the tip of me coming around, and so he was able to shoot me. Like, yeah, like within the story that you're pretending, yes, but like that's nothing whatsoever even slightly like it. There's a bunch of code, and because the intersection of some ray hit a bounding box, you know, because, you know, like you have a gun and stuff, just super quick, just to illustrate like how simplistic AI tends to be. You know, you're standing there with a gun, right? Like something should, you know, going through should be able to shoot here, but approximately nobody ever implements that kind of thing, because in order to do the sort of calculations to see whether or not the thing has actually intersected with your body or not, the amount of math you need to do to look at all of the polygons that make up the model of your body with the gun and stuff, it would cause the game to grind to a screeching halt. So instead, what they tend to do, often a little bit more sophisticated, is they'll use hemispheres at the top and bottom. It's called a capsule. It's a hemisphere, and a cylinder in between is a little bit more sophisticated than like an outright, like, technically a prism, but, essentially like a rectangular cube. But like same basic idea, like a super simple shape that you can just tell whether or not a line intersects with this super simple shape. Like, that's the kind of thing that often happens, but it's so close and you don't see the particulars anyway that it's more than good enough for having fun, which is the point after all of video games. Now, the sort of AI that's probably motivating this question are the large language models that have become popular in the last few years. Now, there's a thing that I'll need to explain, although I'm going to massively oversimplify it so that this does not become a math lecture. And you need to understand, from the field of linear algebra, there are these things called matrices, or a matrix, plural matrices, which are just a grid of numbers, just rows and columns where it's numbers in each cell of that. And there are particular ways that you can add these things and multiply these things together. And the relevant thing is that multiplying these things has a sort of it's incredibly simple. It's just, for each cell, you take the column of one matrix and the row of another matrix, and you go through multiplying those, and then you add the sum of all those things together, and that's the result of the new for that cell in the new matrix. And there are particular rules of how you do it. And it's a little bit complicated, but not super complicated. And this stuff does magic. This is the basic heart of all 3D rendering, by the way, because like if you want to take a, they don't have to be perfect. You can have like a 3x2 matrix, for example. And actually, this is really, really useful if you want to take three-dimensional object with coordinates and map it into a two-dimensional one. Linear algebra using matrices, where you apply the matrix to each of the points are essentially vectors are just like one column or one row of numbers, a one-dimensional matrix essentially. And so you can multiply this out, and it can translate these things. It can translate them with perspective, which is the key to 3D graphics. And it's amazing. And they can do a lot of other really, really powerful things. And a lot of where their power comes from is the fact that they are phenomenally, astonishingly calculation intensive. You just have enormous numbers of calculations. But they're all simple calculations, hence the linear in linear algebra. It's like a line. Just the calculations you need to do for a line, nothing complicated like a parabola or anything. Okay, matrices. These are the heart of modern AI, and just really, really, really enormous ones. So if you want to do the kind of stuff I was talking about, uses like 3x3 and 3x2, often 4x4, in fact, but let's ignore that. That's an implementation detail, matrices. Large, like the sort of things that you're seeing really impressive results from in AI are using much, much larger matrices. And the number of calculations go up phenomenally. Because remember, for each cell, you're multiplying a row by a column. So when you make a row longer, you've got tons and tons more multiplications and additions you have to do. And you're seeing a lot of specialized hardware because there's all sorts of great stuff you can do that makes this a lot faster, because it's always row times column done in the same way, infuse, multiply, and add instruction stuff. Won't get into the details. The point is that this is, so you saw this in stuff that was called neural networks, and the term neural in neural network means like a neuron, except they're not. There's, technically speaking, some reasons why these reminded people of neurons. But mostly they don't actually matter, and they have nothing important whatsoever to do with neurons. And basically, the short version is people call them neural networks because it sounded cool. To some degree, it was just marketing and sounded impressive. And those produce some really, really useful results in terms of if you want something. Now, remember, sense 2 of this is a thing that does what human beings would use intelligence to do. If you just want the task done and do not care how it's done, and you have massive computational power, which we've gotten some pretty substantial computational power these days, especially thanks to GPUs. Computational power remarkably useful for doing things like linear algebra, because the primary purpose of a GPU, the graphics processing unit in your computer that does the 3D stuff, is to do linear algebra. So that actually really helped to get going a lot of this stuff, because you could use GPUs to do a lot of this work very efficient, very cost effectively, and to do truly insane amounts. Because remember, like at 60 frames per second, 60 times a second, you're doing all of the linear algebra to translate literally millions of polygons into pixels that you can see that look like a 3D, image of a three-dimensional space. And so that really, really helped, although we're getting even more sophisticated stuff. And the point of this is to illustrate how many computations are being done, and in consequence why this is useful, but also why that can be misleading. So just to sort of, the epitome of this are, we're getting to these, they're so-called wafer scale chips. CPUs are fabricated on these wafers of silicon. And normally you get like several hundred on a wafer, and you cut the thing up into individual chips that you then repackage to sell individually. The wafer scale chip essentially takes them all and then uses the fact that they're next to each other to make them able to communicate with each other incredibly quickly. And this is sort of like the epitome. Different groups have been designing these wafer scale chips that can do these sorts of calculations truly astonishingly quickly and relatively cost effectively compared to buying that number of GPUs if you cut it all up and so on. But to put this into perspective, like one of the wafer scale chips that I saw, that I was reading about, consumes about like 20 kilowatts of electricity. So on one side, you hook up the massive cables necessary to bring in 20 kilowatts of electricity. And this is low voltage, by the way, which means enormous amperage. For those who know what that means, don't worry about it if you don't. On the flip side, you get a tiny bit out of it, but not a lot. On the flip side, you have to pull 20 kilowatts of heat out the other side. And bear in mind, like the space heater that you plug in onto your desk is about a 1.5 kilowatt, like warm yourself up or to warm up a room. That kind of electrical heater is generally around a 1 to 1.5 kilowatt heater. This is pulling the equivalent of, like somewhere between about like 12 and 20 of those heaters worth of power out of a space this big. So, that's the amount of power. And the reason I'm bringing this up is because gives you a sense of the scale of the amount of computation that is being done. It's truly, truly astonishingly large amounts of computation. And the point of all of this computation is, roughly speaking, that you set up these matrices. Then you have ordinary code, which takes whatever your input problem is, whether it's text or images or whatever, feeds it into these matrices. These matrices do calculations and out comes something that you then have other code which interprets as an answer. So you can put in images and then interpret the calculated values as image recognition. You can put in stuff and interpret the output as things about images. You can do image-to-image transformations. You can do, textual type stuff. Now, the thing about these things is you have to get, for these, and these matrices are truly, truly giant. You have to have numbers for all of those things, and what those numbers are determine how the neural network functions. And you can have multiple of these matrices, by the way, where you then, depending upon what you're doing, you pull in different ones and multiply the output, the input by the output, etc., and things like that. The output becomes the input to the next one, and so on. Do lots and lots of these matrix multiplications as appropriate. Lots of different techniques depending upon what you're doing, but all fundamentally it's just matrix multiplications. It's all stuff you could do by pencil and paper if you had an unimaginably large amount of time. Adjusting the microphone slightly. So the point of this is that ran into limits, though, because the general approaches for how you did this involved, you have to come up with these numbers. I'm getting ahead of myself slightly. You have to come up with these numbers, and that's called training. That's where you take input data and sort of an output state, and there are techniques for how you then use the output state that you want and the input data, and basically use that to come up with all the numbers. And generally it's an iterative process where each new thing changes all of the many, many numbers in your matrices very, very slightly. And so you have tons and tons and tons and tons of them that go through, and then eventually they work their way through changing these numbers. And then eventually you decide, like, okay, that's trained. That is to say, that's the matrix I'm going to use. And then you actually use it to do whatever you want, and you get whatever quality results that happens to produce, often highly variable. Okay, so that is like what's going on. There was a kind of a revolution. I believe it was like 2019. Someone, if I recall correctly, from Google put out a paper on what they called the transformer. Oh, I'm sorry. This is the part that I jumped ahead to, and now I'm skipping past it. This is a bit of a slow process, because it involves insanely large numbers of calculations, far more than actually using the thing. And the second part is, in general, the techniques all involve, like, you take, so like, let's say you want to train on 1 million images, which is not a very large number of images to train on, by the way. So bear in mind the numbers involved here are truly huge. You want to train on 1 million images, which is not a very large data set. So you train on the first image, and that makes whatever modifications. And then you train on the next image, and that perturbs everything it changes things very slightly. And then you train on the next image, and that changes things very slightly again, and so on, going all the way through until you finished with your 1 million images. And this takes a very long time, and it's all computationally expensive. And so this limits how big your training set can be. Basically, when you want to be finished with training, would limit how big your training set could be. Because if you want to do 1 billion images, well, it'll take 1,000 times longer than 1 million images. And if 1 million images takes you 6 months, well, to train on 1 billion images would take you 6,000 months, and you'll be dead before it finishes. So, that's kind of not good enough. I mean, statistically, I think if you work that out, that's only like 50 years or something. But anyway, I was making the numbers up on the fly. You get the idea, because the numbers are for illustration purposes only. Somewhere around 2019, and there might be 2020 or 2021, but I think the number 2019 sticks out in my memory. Someone, and I believe it was from Google, published a paper on what they call, on a variant of this called the transformer. And the big thing about the transformer, just a name for an approach for this, is that you can train the thing in parallel. That is, you can run many, many copies of training on input data, and then there's a way of combining the results afterwards, which is way less computationally intensive. And that meant that instead of having to run your one computer training this thing and do 1 million of them in sequence, you can have 1,000 computers each doing 1,000 images. And so, in our example, if training on 1 million images takes 6 months, you can have 1,000 computers training on 1 million images, and at the end of 6 months, you then spend a little bit of extra time to combine the results of all 1,000 computers, training from all 1,000 computers. But now you've trained on 1 billion different images. And that's where the modern explosion has really come from, is the transformers, because they enabled you to get much, much, much larger data sets. And these things all, in general, benefit from the data sets being much larger. There are other things too, like the exact size of the matrices can be larger, because like the bigger the matrices, the longer this takes. But if you can parallelize it, then you can trade money for time, essentially, and like use bigger matrices, which will get you better results in a lot of cases. Broad brush I'm painting with, right? But run it on, but it costs 100 times as much because you're running on 100 times as many computers. So there are various trade-offs, but the big thing was these transformers allowed you to use much, much larger data sets, which helped tremendously in terms of the quality of the output. And so that's where, ChatGPT may be the best known one, GPT-3, GPT-4. GPT, by the way, stands for General Pre-trained Transformer. General meaning all topics as opposed to one particular topic. So like they didn't just like select down to like, types of cancer or something, and like all literature about cancer, but nothing about art, right? General just means all subjects. Pre-trained meaning that they trained it ahead of time, kind of like what you normally do in common, okay? And then the transformer being they're using this kind of model, and this is using the transformer is what allowed OpenAI to train on basically literally all the text they were capable of pulling from the internet. Because they traded money for time and did this in truly massive parallel, and so they were able to pull all this in and then combine it, and so then the results was something that works really well. Now I'm just going to talk about there are a lot of there are differences, but a lot of similarities between how a lot of these things work, and So the important part, and I'm just going to focus on just how ChatGPT works. The same stuff in terms of philosophy applies. It's not the same engineering, it's not the same particulars, but nothing philosophically changes. And that's the question that I'm answering. And it's just a little bit, more people are familiar with ChatGPT, and it's a little bit simpler to describe. So the way ChatGPT works is that you actually, what they did is they encoded all words into roughly 50,000 word, let's call them wordlets. So many things are just words, and it's a little bit like syllables, but it's somewhere in between syllables and words. So there are particular ways for like longer words that you break them apart into sort of these wordlet things, and this produces roughly a 50,000. It's called it's like a vector. So one-dimensional array. That's 50,000. So each word is a 50,000 element vector, which will have a 1 where that in the position that corresponds to that word and 0 everywhere else. Now your sentence turns this into a matrix where for each word you have a column which will have a 1 in whichever word falls right there. So if you say like the black cat, you'd have 3 elements or 3 columns, and the one column would have a 1 where it corresponds to the row, and all the rest of them have zeros. The next one would have a 1 in the cat row and all zeros, and black row, and the next one would have a cat in the all zeros. That kind of thing. It's been a while since I read the paper that explained the particular details of it. I'm pretty sure it's, essentially the rows are the words. It wouldn't matter in the slightest if you were to flip all of this, so that it was columns, etc., and rows were the words. Doesn't matter. Just all your other matrices have to be correct, but you can generally flip all these things, and as long as they're all flipped appropriately to each other, it doesn't matter. Okay, so then they take that as the input, they run this through lots and lots of matrix multiplications, and then out the other end comes a matrix. And then you of the appropriate size, and you interpret this again as a collection of words by looking at, now it's not ones and zeros at this point. It's this is probabilities. So it's like the probability of there being this word here, in this column sort of thing. Become, is the output here. And then there's, you can pick the highest one, or they have something called heat, which will actually sort of randomly pick, weighted by the probability of the thing coming out, and the higher the heat, the less likely you are to pick the most likely, and the more likely you are to pick a little bit less likely ones, so you get more randomness. And then what they tend to do, I believe, is they then iterate this. So they'll generate the next word in the sequence, and then they'll take that as the input and generate the next word in the sequence, and take that as the input and generate the next word in the sequence. So in a really technical sense, what this is a random text generator, where the randomness is weighted by the probability of a particular word being what comes next in the sequence, given all of the input training data. In this case, all the training data being everything they could find that was published on the internet. So, because there's stuff that's behind password and stuff they didn't have access to, right? But all the publicly available stuff, they basically scraped the internet back when. So that's essentially what's going on there. By the way, if you ever heard of Markov chains, it's conditional probability, the probability of something given what came before it. And there was 40 years ago, there's a program called Dissociated Press, which used Markov chains, which were much, much more computationally simple, where it would analyze a bunch of text to figure out what is the probability of, given a particular word, what's the probability of, for all the words, what is the probability of it following, and then you pick the most likely word to follow, and so on. And then you could generate, now you could do this based on letters, you could do this, and you can have these as chains, given these two things, what's the next one, and so on. And depending on some settings and how willing you are, and especially if you did this at word level, you could generate paragraphs of text that actually sounded plausibly grammatical. It's the same basic thing, only much, much, much more complicated, with far, far more computation going into it. But basically, it's just a random text generator where it was trained on input text to come up with the probability of words following other words. And the output is essentially the most likely thing to follow the input based upon all the data that was trained on. And as I said, like GPT-3 and GPT-4, there were previous ones, and there's 3.5 as well. There are various things where you can make your matrices bigger and allow for more of them and so on that tend to get you better results. As well as if you can get more training data in, that really helps. What we're really seeing is the more training data. GPT-3 and 4 and so on is showing like the effects of like throwing more computational power at it, more memory, more disk, etc. So so as you look at that, what's going on? Well, basically it's a random text generator that happens to produce text that is very like this sort of text that existed on the internet circa like 2019, 2020, 2021 was I think when they froze it or something. Anyway, but the point is, it's randomly generating text that's a lot like it, that looks very similar in terms of like the patterns of what comes out. And the thing is, because these like the various probabilities of words following other words, and because these things are matrices, by the way, word position becomes significant. So that's like one of the things that makes this so much better, is that like, word position and the words that are around it. So like, I tipped the waiter and I tipped the cow. Different words tend to be associated with these things when you have like, tip and cow nearby to each other and tip and waiter nearby to each other. And you see lots of different words in input texts. And so the probability of these things, because ChatGPT tends to use a window of 4,096 words. Those sort of wordlet things. But anyway, and so as a result of that, it's... As a result of using that, you get a lot of information of the interrelationships of these things being nearby to each other and so on, whether or not they come in the same sentence or different sentences, and so on. And so it does a really, really good job of getting essentially pulling the right sort of text to get these probabilities from, because of the interrelationship of being nearby, and also the way that English is... English is a positional language, and this makes position significant, because, which column you are very much influences how the matrix multiplications happen. So now, in like a decline language like Latin, you would have different endings, and those would become different wordlets and so on. So you'd get, essentially similar kinds of things there. So the grammatical structure gets embedded in the ordering of these things, and that's part of why this is so much better than previous attempts like this had been. And the end result, essentially, this fools a lot of people, because basically the text that is highly probable, based upon the inputs, will carry with it the meaning that the people who originally thought these sentences out and did them with intelligence like we have, put into it. And so you'll see those same, because that intelligence is communicated through patterns, and since what is being done is essentially pattern analysis and pattern replication, the patterns that were used to express these ideas will show up again, and so it will feel a lot like this thing has ideas. And this is where a lot of the both mistakes as well as propaganda of like, oh, this isn't sense 2 of artificial intelligence, this is sense 1. Clearly it thinks and clearly it understands. And no, it doesn't at all. And like the fundamental problem for a lot of the ways these things try to get used, and this is a little bit of a side note, but kind of relevant too, is that there is nothing within the model. All the model has is the probabilities of words following other words. That's literally all that exists within the model. And so there's no model for meaning here. There's no concept of, there's nothing within this that has a concept of the world as entities that have, natures and relationships to each other and so on. And as a result, it will generate utterly ridiculous things, because it just has nothing, there's nothing in the model for it. It just so happens that if you make your text look quite a lot like the sort of text that human beings who did have these things generate, the resulting text will look a lot like it has these things. But it's really easy to push up against, its limits, and where it gets this wrong and doesn't understand things. And it makes it obvious that it doesn't understand anything that it's saying. And the, so, like, and this is where you get to some of the limits of it. Like, basically, AI is a this kind of AI is a really great tool for anything where it is fine to be statistically correct. So, if it is found to be statistically correct, for example, image sharpening. AI methods have been really, really good at image sharpening because as you are modifying all of the individual pixels, if a few pixels are wrong or even very wrong, not really a big deal. Not when you have millions of pixels, it doesn't matter. I mean, the way our eyes see things, you get some pixels fairly significantly off, and what does that matter? Especially when this is sharpening for aesthetic preferences. Like you do run into some problems like this if you're trying to use like AI image enlargement, where the AI will essentially like create stuff out of thin air if you're trying to use this to prove what was in the original picture. That's really quite a problem because like then it matters that the AI was wrong. But on the other hand, if you're just like trying to make the thing look really nice, well, then AI tools are phenomenal at that because it's fine to be wrong as long as like overall you're mostly right. Because that's what like looking at a picture and it being pretty, like that's, you take a picture of a landscape, like if you're not using it for forensic purposes, but just for, the aesthetic value of it, like the thing depicted in the picture, it's only a picture. It's not the real thing. You're not doing anything with this. So if it's slightly off and like the thing is not quite that, whatever. It's still basically right. That's good enough for the purpose. Denoising sound applications, right? There's been great work in removing, fan noises and other kinds of noise like that from recordings. And again, like, if you're very slightly off, if you're off there, every now and again, and 48,000 samples per second is pretty good. 44,100 is common, so it's 48,000. Anyway, like that number of samples per second, if a few of these samples are fairly off, like basically you're introducing supersonic noise, so who the hell cares? Because like, most people can't even hear levels of supersonic noise like that, so it doesn't really matter. You have to be really young, like the noise, the highest frequency you can hear is like, it's around like 20 something kilohertz when you're really, really young, and like it fades down to around, depending on, assuming you don't have like massive hearing loss, it fades to like 16 kilohertz, and 14 kilohertz, something like that, and as you get really old and particularly super high frequency hairs die off basically. So there's like, anyway, sorry, I was just nerding out on you, but point being, again, like, you get something wrong like that, who really cares? But AI of this kind will be confidently wrong. It will produce wrong answers just as happily as right answers. Unlike human beings, who, like, when they're not sure of things, will actually take the trouble to tell you whether or not they're sure. Because they have things like understanding. They're not just probabilistically generating results. So, I mean, in one sense, by the way, an interesting model is that essentially AI is like a really, really good bullshit artist. And there is something there, like it'll be very, very confident. It's really good at making the pattern of what it's saying look right, even though it doesn't like have any clue about the substance. So you can find bullshit artists who can give you a lecture on some topic they know nothing about, and they're making up as they go along, and they're just so confident, smooth, and they remember what they said. And if you don't know anything about the subject, it sounds phenomenal. They've gotten the pattern right, the probable distribution of sounds is great. It's just there's no content there. Same basic thing. So wherever that's fine, AI is actually a phenomenal tool. Things like enlarging and doing edge detection, it's great at it. It does a wonderful job. Now it's very, very computationally expensive, so there is a trade-off there. But computation has gotten cheaper and cheaper, and we can afford it in a lot of cases. So there are a lot of very useful tools like that. And you're seeing them being used. I know a programmer who uses this kind of text generation stuff because, like, GitHub Copilot, I'm told, is quite good because, like, they've done what. Now, code always has to be correct, so it doesn't do code. You don't trust it. It proposes things that may be right or may be wrong, and they make it super easy to ignore when it's wrong and only use it when it's right. And when it is right, it saves you a bunch of effort. And so, like, that's a useful tool because, this is only being used when the person doing it knows that this is correct. And it's only ever generating, like, relatively small little things. And there's stuff in programming where, like, it's like just a standard pattern where there's no real thought that's involved. And this actually works out very well because, like, that's the stuff that's least pleasant to program. And the stuff where you have to think is actually the most pleasant part to program. And so tools that will generate the kind of brainless, repetitive, just pattern type stuff, those just make life easier and make you more productive. And it's helpful, and it's really easy to verify that they got the pattern, the basic brainless pattern right. So, you'll see tools like that as well. You already see them, and they're being used. There's GitHub Copilot. I don't know if it's actually cost effective, or if they're... I am going to explain this, or if they're just seeking investor money. But in any event, it's a paid service that you can use. Some people do and find it very useful. And so things like that are going to happen. The big revolutionary stuff is not going to happen because it's not sense one, it's sense two. And something very much, just to look at the current thing, and will become dated over time, a phenomenon that you'll see invariably is there are two main ways in modern economies of making money. One is to sell things to people, and the other is to sell things to investors. And this is especially a technology thing. Oh, you see it all over the place. Basically, if you can get people to invest in your business where you get some of that money, like pay yourself a big salary or whatever, or they buy out your, you own stock in the company and they buy your stock out and so on. That can be a phenomenal way of making money. And you don't have to sell things to people who are actually going to use them. You just have to convince people who have a lot of money that you're going to eventually sell things to people who want them. And then you get their money, and if it doesn't work, oh well, they're the ones who get screwed. So making money off of investors is a thing you see, and there've been a lot of cycles of it. If you I've seen a bunch of them, like the whole .com bust of the early 2000s was a fascinating example of this cycle where people were pouring money into all sorts of stuff, and it was really hot, and investors were really, really chasing it. And lots of people made money by just looking good to investors, getting a bunch of money in their company for a while, making sure they got a bunch of compensation for it. Then when the company goes bust, it's the investors' money, not theirs, and they made off with some of it. Much easier than making a product that actually works and selling that to people that you'll have to support. So you see the same thing with AI. You're seeing a bunch of stuff where people are chasing investor money, or companies, when I say people, are chasing, people within companies are chasing investor money, not customer money. And so they're announcing all sorts of AI things because it really makes the investors happy, and the investors pump money into the company. And that means they get nicer, all the benefits of money. And so this is a thing that will heavily distort. Anytime you have something new like this that people can show as having a lot of promise, you will see tons of investor money coming in, lots of chasing of investor money, tremendous distortions in the market, and enormous amounts of overpromising as a result, because overpromising really big isn't good with customers, but it's phenomenal with investors. Very, very helpful. And as a bonus, as long as you're not straight up committing fraud, investors have a very hard time suing you for overpromising. So just make what you're saying, relatively clear that what you're talking about may not happen. And investors are held to much higher standards of knowing what the hell they're doing as well. Customers are considered to be ordinary people. If you're investing large amounts of money, in general, the regulatory bodies figure hey, it's on you to make sure that you're not screwed over. We're just here to prevent things like people outright lying. We're not here to learn the stuff that you should be taking time to learn. Whereas ordinary people have a limit to how much they can learn on, a wide array of subjects. And so ordinary people need greater protections than people who are professionally investing their money. They just are supposed to know what they're doing. And that's, the flip side of getting to make a lot of money this way is you're on your own, watch out for yourself. Again, I'm massively oversimplifying. Having political connections helps, yada, yada, yada. Point being though, the chasing of investor money looks fairly different than chasing of customer money and is highly distorting. And if you mistake the chasing of investor money for the chasing of customer money, you can badly misread what's going on. To give one concrete example of this, when OpenAI released ChatGPT, their official statement was that they're doing this to collect data to improve the model. And I have no doubt that they did use some data to do it, but my own cynical take on this is that they did this as a massive publicity stunt because the amount of money it was costing was insane. The CEO of the company described it as our server bills are eye-watering. And if you just know anything about what it's like to rent server space, which I have to a little bit professionally, just dabble my finger in it, not in the big stuff. But, I've looked at some of these things and sort of like what renting servers scale and what renting, they use like $10,000 GPUs and they need like 4 of them. Anyway, point is, if you look at what renting this kind of stuff actually costs, it was incredibly, phenomenally expensive. Much more so, in my opinion, than not knowing anything insider. I don't have any, slam dunk evidence. But to my eye, it was way more expensive than made even the slightest bit of sense in terms of the degree to which they could improve their model by having various people do things like ask it to use a sentence that doesn't include the word apple. But, or a sentence that ends in the word apple, et cetera, et cetera. But what it did make a lot of sense to me as doing is generating a lot of buzz to attract a lot of investor attention, because a lot of people thought it was cool and a lot of people thought like, oh wow, there's all this stuff that we can do with it, and this generated a ton of investor interest. And indeed, Microsoft put billions of dollars into OpenAI to license their technology for things. And it made, again, I don't know this is not I don't have concrete evidence that this happened. I don't know for sure that this is what is going on. This is just my reading of the situation, having only completely outsider information, just the public information that's available to everyone else too. This is my take on it. But it looks very much like that. It looks like that kind of thing. And if you read histories of other stuff, you'll definitely see stuff that was there to chase investor money, not to chase customer money. And there's all sorts of interesting distortions in other stuff. This would be a tangent to go down sort of like one sentence on this. There are a lot of things where the basic business model was, let's use investor money to run a free service for years, building up hundreds of millions of users, and then down the road we'll figure out some way of making money off of this, because how can you have hundreds of millions of users and not be able to make money off of them? And we're seeing all sorts of interesting changes in those services now, as they have to actually make money and can't just run off of investor money. Twitter, the thing Elon Musk likes to call X, is a really fascinating example of that if you go into that. So that's another place where you can see the kind of investor distortions that go on in markets, and then apply that to the AI kind of thing, to look at the kind of distortions that are going on. It's a super hot topic, tons of investor money chasing it, so you're going to see a lot of distortions and a lot of, essentially empty promises too. So that, I think, kind of rounds out what's helpful in understanding AI. That there's tons of AI in sense to things that do what human beings would use intelligence to do. These things are often useful tools. The coin sorter back in its day was a useful tool if you had a lot of coins to deal with. And, modern large language model stuff can be useful tools for all manner of things. I mean, more like the image generation stuff, some of the, image recognition stuff is useful for various stuff. Potentially you can use this, it's being used to some degree in like, certain kinds of safety applications, as long as like all you're doing is like sounding an alarm to make sure a person is awake, because like based on the camera it's looking like they're falling asleep. That stuff has the potential to go bad if you misuse it, if you trust it too much. But as long as you keep from trusting it too much, useful things in image improvement and sound improvement, sound denoising. There's some great stuff that's been done in terms of like massively improving synthesized speech. So there's some great stuff there too, that's been done that's quite useful. All of those, any tool has its dark sides. Any tool can be misused. The stuff where you're generating sounds in somebody's voice in order to try to pretend that they said a thing that they didn't say. It's there's like this little bit of time when the fact that something was recorded makes it highly likely that it genuinely happened. And we're kind of getting back to where, because for a long time you had to know your source. Like somebody tells you like, hey, so and so did such and such. You're like, okay, but did you see it? No. Well, who did see it? And, for a while it's like, look, I've got a picture. Pictures don't lie. And eventually pictures lied. For a while pictures lied with a lot of time and effort, like Soviet airbrushing of taking people out. And in more modern times, pictures lie much more inexpensively, and for a while like sound clips didn't lie. Now sound clips lie, and so we're getting back to the ordinary human experience of you have to have a chain of trust on your sources. You can't just trust something because you saw a picture of it or a video of it or sound of it. But that's been the dominant human experience for most of time. There's just like a short little window where you could kind of trust clips and stuff. So in the same way that that saying, you would occasionally hear about, a wise man does not have a reaction until he's seen the unedited video clip. Similarly, a wise man does not have a reaction until he sees the unedited video clip from a trustworthy source who is vouching for that the video represents what actually happened in real life. And one thing about American courts, by the way, is interestingly, they've always had that basic approach that evidence only comes in on the testimony of some human being who will vouch for it, and that you can then evaluate the trustworthiness of. There can be chains of custody and so on, but you always needed somebody to say what this was and what it meant that you could then cross-examine and question and get at, including video and audio and so on. And so that's something the American court system has generally done right. It's got plenty of failings, but that standard is... it's a good one to have, and it's one that everybody should have. There's a little bit of time when you say, oh, come on, you can't fake audio. Well, now you can fake audio. You can fake audio really well. So, yeah, we're back to the thing that, virtually all of our ancestors faced of, why do you trust it? Knowing who to trust. Anyway, yeah, so that, a lot of uses, like all tools can be misused, and, yeah, nothing in it is anything like sense number one, which wouldn't be a problem for Christians anyway, because essentially it would be something analogous to how we take part in making intelligences through reproduction. Which is like, if you just take that for granted, there's more of a philosophical problem to work out the nature of secondary causation there than you have appreciated. But it's basically the same thing. And yeah, I think that really covers the topic in everything I think that'd be useful. So until next time, may you hit everything you aim at. If you like this video, then clicking the like button, according to YouTube, will make them more likely to recommend it to others. If you know anyone who might get something out of this video, then it would be kind to share it with them, or just share it on social media in general. And if you'd like to see future videos of mine, you can subscribe. And if you're not in the habit of checking your subscriptions page regularly, then I suggest clicking the notification bell and setting that to always, because otherwise subscribing to a channel basically just sort of like gives YouTube a hint that maybe it should consider recommending these videos to you, possibly at some point, if they think so. It's a funny world we live in. God bless.